Hi, welcome to one and all. Next, we will be discussing Theorem 8.6, which is a well-known result on used by Ramanujan. But before going to this theorem, let me once more explain what is Theorem 8.5, which we will be using in this theorem. So, in theorem 8.5, we have proved that sk of n, which is given by sigma d divides gcd of n k f of t g of k by d, has a Fourier series expansion of the form sigma m mod k a k of m e raised to 2 pi I m n by k, where akm is given by sigma d divides gcd of mk g of d f of k by d d by k. So by the proof is by using theorem 3.4, where by using 8.4 we have a k of m is 1 by k sigma n mod k just k of n e raised to minus 2 pi I n m by k. In this we first apply the definition of sk of n. Sk of n we will be applying here 1 by k sigma m n equal to 1 to k sigma d divides n d divides k f of d g of k by d e raised to minus 2 pi I n m by k. Now here we are going to separate the terms, the summation, into two, where by using a substitution n equal to cd. When we put n equal to cd, then c will become n by d. Then clearly we can see that the for each fixed d, the index c runs from 1 to k by d. That is 1 to c moves from 1 to actually n by d, where n varies up to k only. So that is why the c runs from 1 to k by d. So here we are going to separate this. Akm is 1 by k sigma d divides k, f of d is taken outside, g of k by d is also taken outside, then sigma c equal to 1 to k by 1 to k by d e raised to minus 2 pi I n m by k, where n is replaced by cd. So now here, if we replace d by k by d in this sum, if we replace d by k by d on the right, we will be getting uh, this fd. This is always possible because this is a convolution type function, so we can always replace this d by k by d and k by d by d. That we can always do. So here also we are going to do that. Here we are replacing d by k by d, so f of this will become f of k by d, d divides k, f of k by d, and g of d, and sigma c equal to 1 to d e raised to minus 2 pi I cm by d. And now what is this? This we have already seen. This summation becomes 0. This is the earlier in one theorem we have studied. This is g of n. So in that theorem we have seen that the result will, this term will reduce to 0 if d does not divide m, and if this will become reduced to 1 if d divides m. So in that case the sum on c is 0 unless d divides m, in which case, so in case of d divides m, the sum has the value d, so this summation will reduce to d, so that this whole summation will become d. So thus akm will become 1 by k sigma d divides k, d divides m, f of k by d, g of d, d, and d by k. That is why the result comes like g of d, f of k by d, d by k. Thus we have proved theorem 8.5. Now we will go to theorem 8.6. In this theorem we have to prove that ckn is sigma d divides gcd of nk d mu of k by d. So what we are going to do is, in the last theorem, that is in theorem 8.5, we are going to replace fk by k and g of k by mu of k. So sk of n is what is nothing but, by previous theorem, sk of n is sigma sk of n is here yeah, sk of n is sigma m mod k akfm e raised to 2 pi I mn by k. So here first we apply this here. So in this part, sk of n is by definition it is sigma d divides nk f of t g of k by d. and here this is the right hand side of that. Here we have replaced fk by k, so f of t will be replaced by d. G of k is replaced with mu of k, so g of k by d will be replaced with mu of k by d. Thus we will get the left hand side. Now in the right hand side, sigma m mod k akm e raised to 2 pi I mn by k, where akm is given by ak of m is given by sigma d divides mk mu of d k by d d by k. How? This is because here we had in the theorem we had that uh, fd g of k by d e raised to minus, sorry, here akm is equal to sigma d divides mk g of d f of k by d d by k. So here this g of d is becomes mu of d, and this f of k by d will become k by d, because f of k becomes k, so f of k by d will become k by d. So that is why here the result has uh, become mu of d k by d d by k. So here this will be cancelled and we are getting sigma d divides mk mu of d. What is this? By definition of uh, this Euler function, we have this is something like 1 by mk. When d divides n, mu of d is 1 by n, and but this is nothing but 1 if mk is GCD of mk is 1, and 0 if GCD of mk is greater than. So in that case this will become summation, this summation will be reduced to 1 if GCD is of mk is 1. So by all other case it is 0. So in those cases when GCD of m and k is 1, in those cases that is n divides nk d mu of k by d. When GCD of mk is 1, we have this will reduce to this summation will be this akm will vanish and it will become 1. So that term is not there. Now the remaining part is raised to pi I mn by k, and clearly this we know this will be nothing but the nth power of the primitive kth roots of unity. So this is by definition ckn. Thus we have proved the theorem. Hope you have understood the concept very clearly, and if you have any doubt you can ask me any questions by using comments or by WhatsApp. Thank you very much for your patient listening.